Today, we want to continue our discussion of triple integrals. I know that there is a problem in play at the moment, the volume of our circular paraboloid. Z equals x squared plus y squared at a height of 9. We still want the volume of that circular paraboloid demonstrated with a triple integral in spherical coordinates. We specifically requested spherical coordinates for that one. So while that problem is still in play, I want to talk about comparing a circular paraboloid to a circular cone. I want to look at two comparisons for the two. Because we saw that in the circular paraboloid that we're working with, inside of it, if we flattened out all the circular paraboloid sides, so they're all kind of curvy. If we flatten those out, then we would end up with a circular cone with flat sides. Let's think about what makes those sides flat, and then let's think about if we can justify why those sides become flat. All right. So we might remember from our early work looking at functions of two variables, a circular paraboloid is oops, I'm going to skip the coefficients. Just worry about x squared plus y squared. So we know that z equals x squared plus y squared is going to be a circular parabola. We clearly get circles, because if we pick a constant value of z, we get x squared plus y squared equals z squared. So our contours are circles. But if we look at things from the positive line, we'll see z equals x squared. So we'll see that parabola from the side. So we have circular circles. The z level curves are circles, because it'll say x squared plus y squared equals constant. And our level curves in other directions will be parabolas. Our other level curves are going to be parabolas. Either z equals x squared plus some constant, or z equals y squared plus some constant. So think back to the beginning when we were analyzing a function of two variables or an equation involving three variables. One of the ways that we can get a picture is to draw level curves. Pick one of the coordinates and make it constant for various values. Z equals 1, z equals 2, z equals 3, and so on. If we want to make a circular cone, we need to get rid of that rounded side. We need to get rid of the z equals x squared plus y squared. We need to get rid of those rounded sides. But we still want to have circles for constant values of z. The way to flatten out the sides is just take the square root, or just square the z. If we have z squared is x squared plus y squared, Then we get z, then we can, if we try to solve for z, we get z equals plus or minus the square root of x squared plus y squared. In this case, our z level curves are still circles. Our z level curves are still circles, even though z equals plus or minus the square root. If z is constant, oops, z is constant. If we square both sides, this will tell us x squared plus y squared equals whatever that constant is squared. And a squared constant is just a constant. So moreover, we can see that our level curves are still circles, and the constant value of z will be the radius of that circle. So our z level curves are still circles. The other level curves have this form z is plus or minus the square root of x squared. Question? If you want the sides of the cone to get steeper, you could adjust the constants. How to adjust the constants will become clearer once we start looking at the other level curves and see the shape of the other level curves. So if we look at the other level curves, so if I take z equals x plus or minus the square root of x squared plus some constant. Now we're looking at functions that have to form the square root of x squared. These are almost inverse operations of each other. Almost because because even exponents do not respect negatives. Even exponents take the negatives and make them positive. So what happens if we can look at a particular value of the x squared? Let's just worry about the plus and where the constant is equal to 0, just to get an idea of what the function is going to look like. So if we just simplify this and take a look at one particular level curve where that constant is equal to 0, and so we're using y equals 0, and we're going to look at what happens in the xz plane. And let's also just look at the positive square root. What we're getting is the square root of x squared, which is another way to find the absolute value of x. So here's what our other level curves are going to look like. Absolute value. So whereas in the circular paraboloid, looking at things from the side, we see a bunch of parabolas. The other level curves, The right circular cone is going to look from the side like an absolute value graph. So in two coordinates, the circular paraboloid is z equals x squared plus y squared. The simplified version of that would be, say, z equals x squared. We know that's a parabola. But the right circular cone is z squared equals x squared, or z plus or minus the square root of x squared, which is plus or minus the absolute value of x. So we get this V shape, and that's where we get this, the straight sides of our cone. Good questions. So notice that the coefficient of the x is going to determine how steep the sides of the cone are. So if we have z equals m times the absolute value of x, we'll have sides with a slope of plus or minus m. So the coefficients of x and y are going to determine the slopes in any particular direction of our cone. So if we want our cone to be narrower, then we would increase the coefficient of the absolute value of x. If we want our cone to be flatter, we would decrease the slope. Question? How's everybody okay? So if at this point you're thinking, Leach, you wound the Wayback Machine way too far, this is an algebra question. That's okay. We're just going over it again. But not everybody's pre-calculus and algebra classes talked about these things in this detail. For the most part, we tend to focus on having you do tricks rather than understanding what's going on. Take a look back, take a moment, look back at your mathematical training up to this point, and how much of it has just been a trick. When you see this, do this. When you see this, do this. And I should take some responsibility here. We're just trying to program you with some predetermined response. A lot of times this happens in algebra. That's the first time where we try to teach you some underpinnings of things and say, oh, now take what you know about arithmetic and adapt it to this new thing called algebra. And you say, and you claim that this looks totally different. And so in your mind, math fractures into arithmetic stuff and algebra stuff. But there's no difference between the two. The algebra stuff is all arithmetic stuff. Everything that you did in algebra was a thing that you did in arithmetic. It's just instead of being base 10, like we did in arithmetic, we're now dealing in base X in algebra class. I guess there are some weirdo things that we do in algebra, because now we can make relationships between variables. But mechanically, every time I asked you to simplify an expression in your algebra class, I was asking you to do some arithmetic. Questions? Think back to rational functions. Take a step the Wayback Machine to algebra, probably an intermediate algebra. Some schools will call it algebra 3-4. Other schools will call it algebra 2 because there's no standardized practice. Some schools will say elementary algebra and intermediate algebra and never have an advanced algebra, which is really confusing. If it's intermediate algebra, what's in between? It's probably a good thing that I wasn't allowed to build a school, because algebra will be organized into belts. In fact, first algebra class, you're a yellow belt in algebra. And then I don't know what comes next because I've never paid attention past that. But there'd be different levels. So I don't know what your rational expressions, historically, your rational expressions were. But a rational expression, an operation on rational expressions, just like one that we did today, say 7 over x minus 2 plus 5, no, 3 over x plus 5. Adding rational expressions. There's nothing different between, the only difference between this problem and this problem I needed another number and I keep coming up blank. Jeez. The only difference between these two problems is that one is a rational expression and the other one is just fractions. Operationally, there is no difference in what you have to do. You're doing the same thing. That whole chapter in algebra where it's like all rational expressions, here's how you do it, should have been, hey, remember fractions? And you'd be like, oh, yeah, kinda. And hey, remember last week when we were talking about polynomials? You'd be like, oh, yeah, a little bit more. It's like, oh, just combine those two things. All right, see you tomorrow. That's it. Rational expressions, simplifying them, is all about fractions plus polynomials. That's it. You do the same thing. And if you're in my presence, you do not call it cross multiply. Cross multiply is used in too many contexts. It doesn't mean anything. So don't say that. That's terrible. If you're working as a tutor, don't say cross multiply. Knock it off. It's bad. You're trying to train your students to visually manipulate things without understanding what's going on. Any questions? Now that y'all are adults, you have to understand what's going on. You can't just do tricks. Like my dog doesn't understand English, but we can make it look like our dogs understand English. If we're like, oh, sit, and you're like, sit. But if I'm like, oh, Colson, I would like you to take up a seated position, please. I said the same thing, but he doesn't speak English. So he's like, oh, I don't know, what the fuck is that? But if I'm like, oh, sit, then he'll know what I'm doing. The way you cheat is you do something visual. You'd be like, oh, sit, or the way that you stand, the way that you approach the dog and stand next to the dog, that will tell him to sit. So if I square up against the front of my dog and I look down at him like this, he'll be like, oh, okay. So I can make it, Colson, I would like you to take up a seated position. And then he would sit. And people go, wow, he doesn't understand what's going on. He responded to this, or the word sit. You know what I mean? I know that's a little bit insulting because you thought you were good at algebra, but I just wanted to demonstrate that you might not be. Any problem? Similarly, like if I actually do x minus 2 times x plus 5, that's the same as if I asked you to do 8 times 15. You perform the same operation. So let me do 18 times 15. You put the things together in the same way. Anyway, what are we talking about? Oh, yes. I wanted to introduce the idea of compare our circular paraboloid that we've been working with for a couple of days. I wanted to compare that to the circular cone that we're going to be working with today and tomorrow. So I picked this cone. I picked a cone because we can actually calculate the volume of the cone. So we have something to aim our integral at. Make sure that our integral coming out has been written correctly. So we know that the volume of the cone is 1/3 times pi times the radius squared times the height. So 1/3 of 12 is the 4 times 25 is 100 pi. So we know what we're aiming for. Actually calculating the volume of the cone is not the question. Building triple integrals in rectangular, cylindrical, and spherical coordinates, that's the question. I dropped this earlier, so it's a little bit dented on the side. Try to fix it there. And you can see the damage over here. Now it looks like I'm trying to shade it, but I'm not. The inverted part just means that I want the tip at the bottom, like an ice cream cone. Let's see. My recommendation is that you put the tip of the cone at the origin. You can put it anywhere you want. That's the only place that really makes sense. So I would set up my coordinates with Z vertical up through the middle of the cone. So that's my recommendation. That you set your coordinates up, that you set it onto coordinates. Oh, I asked for coordinates. You have to put coordinates. So now I'm just going to direct you. Put the tip of the cone at the origin and write triple integral for the volume of the cone in rectangular coordinates, cylindrical coordinates, and spherical coordinates. Now notice that we do have still a circle, but the slope of the side, it looks like we're going to increase by 12 over 5. So that might adjust what we have to write for our, adjust what we have to have for our coefficients. So what I want you to do is take this problem. Think about what the coefficients are going to have to be for the x squared and the y squared to make sure that we get the right cone from the side. So make sure that when you look at it from the side, from the side view, I still have the z-axis going up through the middle. I have just the entire xy plane down here. And all the way around, we still have the base radius of 5. And a height of 12. Figure out where you're going to have to put that 5 and the 12. How are you going to make that slope? How is z going to change with that radius for the 12 over 5? Good questions. All right. I have another example on my list of examples today. I was going to take about 10 more minutes, and I cannot for the life of me remember what it was. Because I just read, so I go, okay, assign this problem. And then I'm like looking at my notes, and it's like, oh, end of transmission. I go, what, dude? It was like 10 minutes of class left. And my memory's like, oh, I don't know. I don't know what to tell you, man. I think I've said before, don't get old. Certain things start to fall apart, like your memory. All right, so this is what we want to work. I want you to start working on rectangular, cylindrical, and spherical. We can use some of the techniques of our circular paraboloid on the spherical. I know we haven't completed that problem, but we'll compare our triple integrals for the cone and our triple integral for the circular paraboloid. Any questions before we adjourn? All right, that's going to do it for today. I will see y'all on tomorrow. Everybody have a good day. And thanks for playing.